I mean, we can hear him.
Okay, so I think I'm going to start. If that's the right thing to do, shake your head yes. Good. Okay, sounds good. I'm Michael Pazzani from the Information Science Institute at the University of Southern California, and I'm here today to talk about expert-informed, user-centric explanations of medical image classification. So let me
That, Michael, we have a bit of technical problem here. We usually start with like introducing the speaker, like tell us a bit of yourself, what did you study, where did you study?
Okay, I'd be more than happy to give a quick introduction to myself. I got my PhD from UCLA in 1988 or something like that. I went to UC Irvine where I met Pat Langley and spent most of my career there. And then went to the National Science Foundation, then became vice president at Rutgers, vice president at Riverside. Went to San Diego, and 2 years ago I came to USC, where I helped start the Artificial Intelligence for Health Center at USC. So, why don't I get started? And this talk is going to focus on expert-informed, user-centric explanations of medical image classification. So, the quick outline. I'm going to talk about medical image classification and give a couple different applications. One's from melanoma, other from radiology. One thing we did is COVID pneumonia, but have done other things like pulmonary edema, that sort of stuff. And currently working with ophthalmologists both at San Diego and at USC on glaucoma analysis. Then we'll talk about the need for explainable AI and talk about then, after explaining why we need this, tell you about my contributions to it. So let's get started. So I'm sure you're familiar with using deep learning and convolution neural networks. Here's an example from 2021 that some people did. Essentially, you train it by giving it images of benign molds and molds with melanoma. It learns to distinguish them. And when presented with a new mole, it tells you whether it's benign or has melanoma with a certain probability. And interesting thing about this paper, but others that we'll see, including my own work, is this either equals or exceeds those of human practitioners on this. In this case, it looked like it did better than just about everyone, one or two people above the dots. Now, I should say, as computer scientists, we spend a lot of time trying to figure out whether the purple dot line or the blue line is better. Should you use VGG or ResNet? Should you use dropout or not? But realistically, all of them do really well, and in this case, better than human practitioners, dermatologists. So that jumps to some of the stuff that I did at San Diego about 2-3 years ago. You may remember way back in March 2020, there was this pandemic, and COVID tests in the US weren't ready, and they were in short supply even when they were. And they didn't really have high sensitivity, mainly due to improper sample collection. At that time, you had to put the collector very far back in your nose. People didn't like that, etc. And we read a paper by an author from China who manually described the differences between COVID pneumonia and bacterial pneumonia. By hand, he looked at these differences on about 100 different x-rays. So we blind emailed him, asked if we could have a copy of his data, and after some convincing, he agreed. And his university sent the worst data sharing agreement you've ever seen. And I talked UCSD into signing that anyway because it was COVID and it might be important. We got the images from China. We wouldn't have received them if there wasn't a faculty member from China walking by my office who helped me solve a Chinese CAPTCHA. And then we were able to download them, and 2 days later we locked down and had to do everything over Zoom. Of course, we used this to apply for an NSF grant on explainable analysis of COVID x-rays. And we actually deployed something within 6 weeks at UCSD that screened patients using x-rays. For instance, diagnosed a airline pilot who had COVID. Um, when the COVID tests became plentiful, we pivoted to predicting COVID severity, who needs to be intubated, who needs to go to the hospital, who can just go home based on their x-rays. The radiologist at UCSD introduced me to some ophthalmologists who were interested in deep learning for detecting glaucoma. And same sort of thing, you have images of the fundus photographs of the back of the eye and try to classify whether they have glaucoma or not, and did pretty well at this also. So then I decided to, pandemic, people reevaluate their lives. I decided I wanted to live near my daughter, who got married, was forming a family. I'd interviewed at USC's ISI in 1983, and didn't work out because I was a UCLA student and that was a USC institute, but always kept in touch with the people there. 39 years later, I called up and said if that job was still open, and it wasn't quite, but we worked things out such that I joined. And a year after that, started the Center for AI Research for Health, basically because health data had become plentiful, and USC agreed to form this. At USC, I met some other ophthalmologists, Ben Ju, Lauren, who works for the Los Angeles County Department of Health. Carl Kesselman's a database person, and more than that. And they had already had a telehealth screening for glaucoma set up where at 17 sites across Los Angeles, patients could have their eyes imaged, and then they would send these eye images to USC, and within a few months, USC ophthalmologists could look at them and help determine if a patient had glaucoma or not. So we wanted to ask, by the way, I'm getting a lot of feedback, and I don't think it's mine, but that's okay.
No, I think the room is actually the audio is finally working, so that's what
That's good. That's good to hear.
Yes.
Okay. So we get this data from the Los Angeles County Department of Health Services. They screen 2,000 people a month for glaucoma, and it has 68% of them Hispanic, 9% African American, 7.5% Asian. And the problem is that they're doing manual screening, and we asked, can AI help? And pretty quickly came up with an AI system that does as well or better than any of the ophthalmologists at this screening. Now, I don't think you can hear the audio from my computer. I don't know how to tell. If you do, maybe in chat you can tell me.
People should stop training radiologists. It's just completely obvious that within 5 years, deep learning is going to be better than radiologists because it's going to be able to get a lot more experience.
Okay, so that's Jeff Hinton saying you should stop training radiologists. And so we're pretty much done. AI solved it all, and we don't really need to finish this talk. But maybe we do. So let me ask a question, and I would like to get thumbs up and thumbs down for those that can do that. Would you trust a robot to scan your back, determine which of the molds are cancerous, and remove them automatically? And not sure if I can see the hands up or hands down, but
I can tell it's really down, hands up.
Okay, well, it turns out you can get very good area under the curve for this. And robotic surgery is pretty well advanced, and robotic surgery in many cases is more accurate than human surgery. So it seems like we should just be doing this, but people have some hesitancies for doing this. Often, my wife unfortunately suffers has fair skin and has had to have surgery to have several molds removed. But usually the doctor tells her things like, that one looks suspicious. It's got an irregular border and the colors aren't quite right. And I think we really need to biopsy that first. And then most likely when the biopsy comes back positive, we'll have to remove it. But it turns out explainable AI, there's a need for that, and we'll talk about it a little bit. But if you look at various medical textbooks or others switching to a different domain, here's a flow chart to determine whether you should get a root canal for something called resorbable tooth. I didn't realize this until it happened to me, but your adult teeth can be resorbed just like a baby tooth and fall out. On an x-ray, they saw my tooth starting to be resorbed and did some more analysis, in this case with a CT, which I wasn't aware you can do for teeth, and determined I don't need the root canal, we'll just watch it. But nonetheless, there's this procedure in the medical literature for how to determine that. And so it would be nice if our AI system, in addition to saying root canal 0.996, said why it's 0.996. Now, there's been a lot of work in explainable AI, understanding convolutional neural networks. Some of the approaches are top-down. They look at the output of the neural network and either look at some activation layers or in some cases propagate all the way back to the input and use that to determine what area of the image is most important to doing the classification. Alternatively, there are some bottom-up approaches that manipulate the image and propagate forward and see how that manipulation changes the classification. Things like obscuring or lime or SHAP, which in some ways is lime with a little bit more sophisticated mathematics behind it. But as I'm going to argue, if it's not worth doing, it's also not worth doing well. And so there's a lot of math behind that, but I'm going to argue that we maybe should be doing something else. So let me show you one of the tools. This is one of the earliest, GradCam, and you can do things like ask, does this photo have a cat in it, or does this photo have a dog in it? And if you ask, does it have a cat, and ask why, it highlights the cat. And if you ask why it has a dog, it highlights the dog. So that's kind of pretty cool. So let's apply this to our cancer again, our skin cancer. Let's imagine now we've got an explanation. And here's the explanation it gives. And I'm also going to, well, maybe we can do the thumbs up and thumbs down as well. But has that convinced you that you'll let the robot remove your mole? And I'm hoping many of you find this not particularly useful.
Yes, I'm nodding.
So there's been considerable progress here. Here's 4 different algorithms applied to chest x-rays. Really neat. They highlight areas and things like that. But I would argue at best they're doing half the problem. So here's what happens in, I'm going to do some things from bird classification. By the way, if I was up in Palo Alto, the Baylands Preserve in Palo Alto is a nice place to do our bird watching. And others from medical images, so glaucoma, trying to find the spot, or melanoma, or COVID x-rays. And when you look at these, and then you compare to what you can find in medical journals or bird watching guides, and it's much, much different. What they tend to do is highlight features or point things out, but they also label them. So in the bird watching, you have to have a crescent-shaped thing on the face, and that's a sign it's this bird. Or for glaucoma, you have to have PPA, which is what those white arrowheads point out, or rim notching, which is what the black arrows point out. Or in melanoma, there you have to have milky white streaks and atypical pigment networks and things like that. My argument would be, instead of teaching radiologists and dermatologists how deep learning works, we ought to teach dermatologists and radiology. We ought to teach AI how dermatologists work or how radiologists work and get their systems to output things like they do. So this is a somewhat opinionated view of explainable AI, and I'd argue that most explainable AI is developer-centric. It explains how AI works to people, and it's somewhat useful to people with a background in AI, but I'd argue it's much less useful if you don't have that background. But furthermore, explainable AI has invented whole new forms of explanation that hadn't existed previously, in spite of centuries of work on explanation in both philosophy and a couple decades at least in psychology. And furthermore, when explainable AI practitioners run experiments on human subjects, they ask these human subjects to act like robots instead of have the AI explain in the way that people do. One recent study had people find 3 words in a restaurant review that lead you to believe it's a positive or negative review of that restaurant, and compared those to words that the explainable AI system identified. Kind of neat, but normally when you ask someone, should we go to that restaurant or not, they're not going to look at reviews and tell you these 3 words. They're going to say things like the service is good or bad. And when you look at this, it's kind of superficial. It says things, well, if the word slow's there, it can't be good, right? But there's a whole trend in upscale restaurants called slow cooking, where they don't half cook your steak an hour in advance and just finish it when you've ordered it, but they actually take a little bit more time to cook it from scratch. And then there's a lot of work on explainable AI. I was funded part of explainable AI, DARPA's explainable AI program. And sorry to bite the hand that feeds me, but for the most part, it compared explainable AI to no explainable AI, but really didn't ask what type of explanation is best, what isn't. Sure, if you show anything on the screen that looks like an explanation, people will say that's sort of good. But what I'm more interested in is, how do you choose among 8 possible explanations? All right, so let me actually tell you one thing that the existing methodology is good for. And explainable AI does some useful things for developers. It tells you if your data set is sufficient. So in one study of explainable AI for melanoma, often when you take these dermoscopic photographs, there's a ruler in the photograph which lets the person judge how large it is. They actually tend to do that ruler more often for cancerous than non-cancerous photos. And one explainable AI system focused on the ruler. So if there's a ruler in the photo, it's cancerous, and if there's not a ruler, it's not cancerous. And these spurious type of correlations pop up all the time. And so, it provides some useful thing to say there's something with your data, but still, it's not that useful an explanation if you've got a good representative data set. So what I've been trying to do is what I'm calling expert-informed explanations and also user-centric explanations. So what do I mean by expert-informed? Well, we study experts. We record them explaining to others, explaining to patients or interns or their peers in grand rounds. Or we look at the we actually have done work on eye tracking to look at what features they attend to. Or we look at the artifacts they produce. So again, if you look at medical journals, you don't find heat maps, but you find labeled arrows in the pictures. And also some of the reviewers have pointed this out to us of earlier papers. They say things like, well, that's kind of nice that you've got that heat map there, but does it have clear clinical correspondences? Or my favorite is, it's not clear the method gives you the interpretation of the feature, it's the expert, the one that looks at the images and the attributes. Now, what do I mean by user-centric? Well, we ask users, if you can choose between this explanation and that, which would you prefer? Or we show them various types of explanation and measure which one helps them learn faster. So one of my grad students at UCSD said she was humbled to witness the contrast between what researchers think an explanation is and what users actually want when we did these sorts of studies. So let me show you some of these studies, and I'm going to switch a lot to bird watchers, and there's one reason. You can send mail to a bird watching email list that has 1,000 people on it and get 25 of them almost instantly to agree to participate in the study for an Amazon gift certificate. And it's real tough to get 25 radiologists to agree to do this, especially during COVID when they were real busy, or 25 ophthalmologists, et cetera. So a number of our studies are going to be on bird watchers instead. So one of the things we did is we showed them birds, and we did eye tracking and looked at what they look at. How can you tell a spotted towhee from an eastern towhee? The spotted towhee's got spots on the wings. And not surprisingly, an expert bird watcher focuses in on the wings, also the eye and some other things. But Or this bird you can tell apart. If there's a lot more black on the face, it's a western grebe. If there's not so much black on the face, it's a Clark's grebe. And again, that's what the experts focus in on. Or we interviewed them. So here's an interview, and again, I'm not sure if you can hear it.
No, we can hear your videos.
You can tell it's a vireo by the kind of a little bit stronger and thicker legs than a lot of than like a warbler. Even though it has the bill is hard to see the shape, but it looks kind of like a thin but slightly thicker bill than a warbler. And then we get to Bell's Vireo by, doesn't have the bold spectacles here, just kind of some faint spectacles and kind of a broken eye ring, kind of weak wing bars, kind of longish tail, and just kind of overall plain gray whitish with maybe a little bit of greenish tones, but not very bright.
Okay, so I'm going to move on a little bit, but what he's basically done is, first of all, he talks about multiple levels in the hierarchy. First, he identifies it's a vireo, and then he identifies it's a Bell's vireo. So that's maybe one of the things you want an explainable AI system to do, not just jump to the correct conclusion, but look at the hierarchy. Then, no question, he's looking at areas, but how he differs from our explainable AI system is he's labeling the areas, or at least discussing what they are. There's a spectacles around the eye, or a wing bar here. And the other thing he's doing is he's contrasting it with easily confused things. So he doesn't point out, for instance, it's got a white belly. Lots of birds have white bellies. But that bar on the wing might be a little bit more diagnostic. Now, same thing with our radiologists.
It's going to be probably an enlarged lymph node, whereas the normal contour of the aorta probably is this as it comes down. So I see that, but there is also overlapping with it some of the branch pulmonary arteries that are doing this. Guys, and there's multiple lobulations, so there may be multiple nodules. Here's another one doing this, all this stuff here. These are nodules, but there's this guy and this guy and this guy and this guy and this guy. There's like, the more you look, the more you see. There's like hundreds of nodules everywhere.
Okay, and what are these nodules indicative of?
Probably metastatic cancer. They're really dense, and they're many and varying in size.
By the way, one of the only good things to come out of the pandemic is doctors are willing to talk to you over Zoom now. You can record that. When we started to think about these sorts of experiments, we were going to have to bring like cameras into their office and stuff like that. And it was so much easier to just do these recordings automatically transcribed over Zoom. So if there's anything good that came out of it. And we thought this was really novel stuff until I started discussing it with Dorit Billman, a psychologist friend of mine, who said, "Do you know what Alan Leskold did in the 80s?" And it turns out Alan and colleagues interviewed radiologists and took transcripts using tape recorders and had people type in what they did, and came to pretty similar conclusions that they're doing things like saying there's a triangular opacity here and things like that. Very interesting things happened before the internet. But we proceed. In radiology, there's a whole ontology of weird shapes and sizes and things, and sometimes people publish journal papers not using AI, but just manually looking at 121 CTs and saying 9 of them have linear opacities and 65 of them have rounded morphology of the opacities, etc. And they highlight these on photographs again. Seems to be a stylistic thing of using different colored arrows and then labeling the white arrow is ground glass, for instance. And it's not just radiology, this pops up everywhere. So if you go to your dermatologists, they've got this ABCD rule of is it asymmetric? How are the borders? Is the color uneven? How's the diameter? Or in glaucoma, they talk about thinning of the rim of the optic nerve head, or hemorrhages, or PPAs, etc. So these diagnostic features are important, and so what we're trying to do is have our AI systems identify these diagnostic features as part of the process. Now let me ask, getting back to some of the human subjects, we asked experienced bird watchers what type of explanation they liked the best, and whether they would recommend using this explanation. So we showed them three different types of explanations: those with heat maps, those with bounding boxes, which are kind of like squares around where the heat map would be, and those with labeled arrows. Now, these were all done manually at first, and after doing it manually, we decided to implement systems that do it in their favorite way. And not surprisingly, their favorite way was using these arrows labeled with diagnostic features. On a scale of 1 to 7, they got a 6.5, where heat maps that's used in explainable AI got a 2, as they like to use that. We also asked undergrads how to identify different types of birds. So on the top of the rightmost one is a common goldeneye. The one next to it is a Barrow's goldeneye. And that face patch is a little different. In some cases, they got no explanation, like in the top. In some cases, other students got these heat map explanations, and other students got the labeled arrows. And we measured the number of trials it took for them to come to the conclusion, to be accurate at doing this classification. And not surprisingly, the labeled arrows was the favorite, or they learned faster when we showed them those explanations than when we showed them no explanations or explanations with heat maps on it. Now, it turns out some people in AI have looked at things like this. There's actually done manually, though. So using a scoring system, they developed, if it has a bluish-white veil, it's worth 2 points, and irregular streaks is worth 1 point, and if you're over 5 points, it's melanoma or not. So you can just look at each mole manually and do that. Well, if you can do this manually, maybe you can do it with AI as well. So we're trying to do that. So now what I've been doing so far is pointing out what's wrong with standard explainable AI. Now I'm going to go quickly over some of our contributions. One set of contributions is trying to more accurately identify regions of interest, which will become important. Another is to look at contrasting explanations, highlight the difference between the two most likely classes, as opposed to just indicate why you believe it belongs to this class. So, why is this a Barrow's goldeneye and not a common goldeneye? And then we'll talk a little bit more about this multitask learning to do these diagnostic features. And I'm going to end saying the common wisdom is wrong. Everyone talks about the trade-off between explainability and accuracy, where I would argue if you do it well, you can have your cake and eat it too. You can be more explainable and more accurate. And we'll see if that turns out to be the case. So the first question we'll ask is, how well does explainable AI find regions of interest? So in ophthalmology, in glaucoma, they actually look at that circular optic nerve head and say things like, is there notching on it? And if so, where is that notching? So in the chart the ophthalmologist produces, they'll say things like there's notching at 3 o'clock, 4 o'clock, 10, and 11 o'clock. So then we can ask if our explainable AI system does things there. And even though we're able to get 95% classification, the heat maps are better than chance, but there's a lot of room for improvement as well. That is, we're not matching what the ophthalmologist is finding. I'll quantify that in some cases. But it's not just us. Some others have done this as well. They've done this in radiology. So in a very nice study, done a little bit more rigorously than the study that we did, they compared 9 different explainable AI algorithms to identifying the location of tumors. And the quick summary is there's a lot of room for improvement. And you look at, there are measures of this. We use things like the intersection between what's predicted and what the people actually say. And we've actually started to collect this in detail in the glaucoma case. So there's 4 different features: notching, retinal nerve fiber, layer defects, PPAs, hemorrhages, and things like that. So we ask them to paint it on the image, and later on we use that to compare. As a total tangent, we had 4 ophthalmologists do this, and we layered the images on top of each other. And in some cases, we have longitudinal data of patients who have progressed in glaucoma. And I'll show you this tangent here, which is these are images of different features that the ophthalmologists found. The fifth column is all the features superimposed. And over 8 years, the patient got worse and worse. And in some ways, that shows up on the screen that the patient got worse and worse. By the way, I'd want to use the third ophthalmologist. I really like what he produced. He found the nerve fiber defect soonest. And if you find glaucoma early, there's various treatments you can do. You don't cure it, but you stop it from progressing. And so the earlier, the better.
How frequent are these measurements?
I'm sorry, I didn't get the question.
How frequent are these measurements?
Typically, it doesn't progress that rapidly. Typically, yearly, 6 months, or every 2 years, depending on how quickly it's progressing. This is about 8 years worth of data every 2 years for this patient. And really, I mean, you wouldn't say they had glaucoma until the 6th year, but there were early signs of it that maybe should have been treated in the 4th year. By the way, these are all people with hypertension, high blood pressure, and glaucoma is more prevalent in people with hypertension. It's an eye pressure. It's eye pressure in the eye also is one of the causes of glaucoma. So I'm going to talk about some other problems we've addressed and then go back to the ophthalmology. So one problem we've addressed is variability in regions of interest. If you run your neural net and ask it to explain why it's a common golden eye, it might produce the explanation on the left. If you run a different neural net, just starting with different random whites, it might produce the explanation on the right. Now, it turns out each of those is somewhat useful features that you can argue it's done a good job, but it sure would be better if it did them both, which is what bird watchers usually do, than one or the other. So how do you do this? One way we've done this is averaging over multiple heat maps, over multiple neural networks. So here, the top shows 4 neural networks, each trying to identify where the wing bar is on this bird. And on average, it does better than any one of them individually. And of course, you know, there's been a lot of work on averaging over multiple models and random forests for accuracy, but you can also produce more accurate explanations by averaging over them. So one of the things we wanted to ask is, can people tell the difference? Can experienced bird watchers, if we show them a randomly selected explanation from one neural network, or the average over 11 neural networks, will they think one explanation is better than the other? We're not telling them these are, you know, how they're produced, but we show them, this is sort of a screen from the trial. We show them the various things, and we're not even calling it explanations, because that's a little highfalutin. We're just saying, are they highlighting the important areas, and asking whether, which highlighting they like the best. And on average, they preferred the average highlighting to any individual highlighting. So there were 28 participants that cost us, about $1,000 to reimburse them in Amazon gift certificates, I guess. They got 24 trials of average Lyme and 24 trials of single Lyme. It's within subject comparison. And they liked the single Lyme on a scale of 1 to 7, 4. But for average Lyme, they liked it 5.5, or they'd recommend it on a 5.5 also. So these are sort of significant things. Now let's see if we can quantify this as well. So now this is looking at a melanoma data set where they had dermatologists identify 5 features on there. So here's a particular cancerous mole, and here's where the white streaks are in the cancerous mole. And then we had our an AI system learn where white streaks are, where the irregular border was, and compared it to what the experts had said. And there's a measure you use, the intersection over the union. So you look at the intersection between the ground truth and the prediction. and you look at the union. If they're identical, that's great, but if they're not intersecting, then it's not perfect. And on average, using the average, produced a better intersection of union over 4 different explainable AI systems. So that was one of our contributions of getting more accurate explanations, and we'll see why that's important in a while. One other thing that we worked on is looking at contrasting explanations. This is the question of not asking why it's class Y, but why it's class Y and not Z. And so one way to do that is look at the evidence you collect for why it's Y, look at the evidence you collect for why it's Z, and then subtract them. Or there's a weighted subtraction as well. So doing this on this 1 to 7 scale of are you willing to use this, people were expert birders more preferred the contrasting Lyme than the regular Lyme explanation here. Both when we asked, is it highlighting the important areas, or would you recommend using that? All right, now I get to talk about my favorite part, which is how do you label these explanations with diagnostic features? So your training data has images where you have the class and optionally a super class and some diagnostic features. So we just ask people, what color wing does it have? And they hit a checkbox, whether it's red, blue, or green, etc. And does it have a long beak or a short beak? We use multitask learning simultaneously to learn the class and detect the features. And then we compute the heat map both for the class or the superclass as well as the diagnostic features. And we could look at the center of that heat map and use a labeled arrow to point to the center. It's a little confusing, so let me sort of illustrate. So this is the sort of architecture where instead of learning one thing, is this a palm warbler or a yellow warbler, you're learning 200 different bird species, but 20 different bird families, and a number of different bird attributes, including bill length, where there's an eye ring. There's about 20 different attributes. We've only illustrated 2 of them on the screen here. So the results of multitask learning, here's 2 somewhat similar birds, a scarlet tanager and a summer tanager, and the system's able to correctly identify them. And one of the key differences is the wing color is black in one and red in the other, everything else pretty much being the same. Now, you can use your standard explainable AI, Lyme or GradCam or something. When we ask it to, why is this a hawk, it focuses on one feature, the bill. If we ask why it's a red-shouldered hawk and not a red-tailed hawk, it's focusing in on both the bill and the wing, or the shoulder in this case, I guess, the shoulder of the wing. Now, putting it all together, if you look at the center mass of the explanation, it's sort of a weighted average of where that heat map is. You can then have a labeled arrow that points to it. So we're able to identify it's an American avocet, which is a shorebird, and it's got a wing bar and a very large bill, and point to the accurate places. Now, I want to point out it's actually important that we do this with the averaging that I mentioned earlier. If you run any neural network on it, it kind of comes close to the wing bar. But if you run 11 neural networks on it and look at the average, on average, it does a better job of finding the wing bar, reducing your risk and reducing the variability as well. So putting it all together, both in radiology, ophthalmology, and bird watching, we're able to identify salient features in ophthalmology like hemorrhaging or notching of the rim or thinning, and have that correspond better to where the experts say they are. And same with the bird watching here, except it thinks that one of those birds is an owl, which kind of confuses me, but that's okay. All right, and again, if you look at either bird guides or even websites with hand-drawn features, how to tell a Hawaiian stilt from a blackneck stilt, etc., you often see these, and so the goal is to produce them, and we're starting to get better at that. Now, let me tell you one more thing that we've done with it. So this is for explainable melanoma diagnosis. So we're identifying these individual features like streaks or negative networks or pigment networks, etc. And doing a reasonable job of that. But it turns out in melanoma in particular, you don't get very representative databases. Many of the melanoma databases have 99% of it is on fair-skinned people. And no question, fair-skinned people get melanoma more often than those with darker skin, but Bob Marley died of melanoma. So people with dark skin can get melanoma. And if you have this unrepresentative data set, you often get non-representative data. So if you look at using a standard neural network, you get 70% accuracy. If you look at the multitask network, you get 82% accuracy. So we're doing a little bit better. And in part, knowing these other features, we think biases the neural network to use the sorts of features that the terminologists use and not pay attention perhaps to spurious correlations that dermatologists aren't using. But what was even more interesting is if we look at dark-skinned people, the standard neural network got 51% accuracy, and the neural network that we did got 76% accurate, still not as good as we would like. But by focusing in on some of these key features, it does a better job, so it's perhaps more fair if you're using the sorts of knowledge the dermatologists use as opposed to coming up with your own reasoning for why it's melanoma or not. So let me end there, take some questions, and the quick summary is there's been, considerable progress in explainable AI on exposing the inner working of algorithms, which is useful for debugging or seeing deficiencies. But rather than teaching experts, apprentices, and novices about AI, deep learning, and heat maps, we ought to be creating AI whose explanations are like those of experts and like those desired by users. And further, you should use a broader set of tools. If all you have is a hammer, everything looks like a nail. Well, if all you have is a brush or a heat map, everything looks like a canvas. And maybe if you use draw instead of paint, you'd have arrows and text boxes and ovals to annotate your images and not just paintbrushes. Here are some papers. I can make that available later on for those that want to track some of this down. Many more coming out now in the medical domain. It was easier to get bird results first. Let me thank you and also thank DARPA's Explainable AI program. Dave Gunning really was very visionary in setting that up. And this nice NSF grant that we got. And here are my grad students from UC San Diego. I do have a new set of grad students at USC who will be involved in the next set of results. So let me take some questions and thank you for paying attention and struggling through the various Zoom difficulties.
Yeah, thank you so much. See if there are any questions. Yeah.
Mike, can you hear me?
Yes.
Pat. Hey, so thank you. This was a great talk, and thanks for reminding everyone about that there are alternatives to what's become mainstream machine learning. Of course, you know, but many people here probably don't know that some of the earliest applications of machine learning were in the 1980s. Donald Mickey, who founded the original Turing Institute back then, had was mostly working with decision tree induction, and this partly grew out of the expert systems movement, where you would interview experts and get them to tell you what rules they were using, and machine learning was largely a response to that. But Mickey had a student, Stuart Shapiro, who sort of combined these two ideas in a way that I think is relevant to what you're talking about. So he was interviewing experts, and he would ask experts, he would give them examples of for a diagnostic task or classification task. The experts would say, yeah, it's a member of this class, and they would ask them why, and they would give them the expert would give features. Well, it's got this and this and this feature in it. But it turned out those features weren't operational. Because the AI system had no way of doing it because it was like on images. So then it would give the expert examples of images and ask them to explain when the feature was present or not. And so they built a second decision tree to classify the features. And they would go down as far as they needed to in order to make something operational. They called this structured induction, which I don't think was a great term, but it was an interactive scheme for eliciting classifiers from experts, multi-level ones, pretty much like you're talking about with old decision tree induction technology. Anyway, that's the historical review. The question is, does something like that make sense here, as opposed to the multitask approach you took, assumed that you had everything up front and you already knew what the features were going to be? Could you use that kind of interactive scheme that Shapiro did within your framework?
So first, that is the most coherent description of structured induction I've ever heard. It always puzzled me. Maybe if it had a different name, it would be better. Let's see. So I guess I'd want to go back and read the 1983 paper again, right? So the question is, can you infer these features from the image? And by the way, I should point out, one of the reasons I use multitask learning, some people, the concept bottleneck models, feed all the diagnostic features into the final conclusion. And what that does is it's almost limiting. If you don't have the right features, you can't do it. So by using multitask learning, you get it to learn some representation that feeds into the final solution. I now sometimes use a joint model where your convolution neural network and your high-level features feed into the final conclusion as well. I mean, there's a couple different architectures for doing this. So I think the idea is there. I will go back and I do recall Stuart Shapiro's work, etc. So I will go back and look at that and think about it. But I think your general lesson as we approach the end of our careers is don't forget some of that stuff in the beginning of our careers, because there were some pretty smart people without GPUs and without high computational resources and other things looking at these
without
problems.
lots of data and without large data sets.
Yes, without large data sets, yes.
Thanks.
More questions? I don't see anything from the chat.
What about monotonicity constraints?
So I mean, there's a whole separate talk I give on how I got, a history of explainability in AI that goes over all that. So I've used monoticity constraints in linear classifiers. I guess I haven't used them here. I'd have to think about how they'd be used, but yeah.
So for those who don't know, you want to summarize the results you had on Alzheimer's data sets?
Yeah. So essentially, what a monoticity constraint does, if you're doing something like linear regression or logistic regression or a naive Bayes or other linear classifier, if in isolation a feature is evidence for something, then in combination with other things, it also should be evidence for that and not evidence against it. So one example where this came up is if you predict baseball players' salary from their statistics, you would think the more doubles, the better, the more home runs, the better, the more singles, the better, the more hits, the better. But because there's correlations between the features, sometimes if you run these regression algorithms, you get negative coefficients for things that should be positive. So the more doubles you have, the lower your salary should be. And so if this were actually true, no player would go from first to second base because you lose $20,000 each time. So you can constrain your regression algorithm to constrain the coefficients to be the sign of the correlation coefficient and have the results come out more intuitive, more understandable. And we ran similar experiments to what we did with the bird watchers on pretend you're an agent, predict the baseball player's salary, showed that people liked monoticity constraints.
but is that relevant to some of these medical diagnostic tasks?
Oh yeah, I mean,
The imaging tasks?
it certainly came up in Alzheimer's as well. So there were certain things, if you shop for yourself, you're more likely to have Alzheimer's than if you don't shop for yourself. And this didn't seem to make sense until you realize Alzheimer's is more common in elderly women than elderly men, and grandma is more likely to do the shopping than grandpa. So it was doing that. It was trying to find some other correlation, but expressed it that way.
Okay, yes, there's no more questions, so we're almost at time. Thank you so much.
Okay, thanks. I wish I came up, but it turns out if I had come up, my flight would have been late, and I wouldn't even be able to give the talk over Zoom. So all's well that ends well.
All right, thank you so much.
Okay, thank you. Stay dry.